Well, good morning, good evening, and good afternoon for everyone. And thank you for joining today's panel. It's our last one this month for Space Transportation Systems. And we have an incredible group of panelists here of experts in the field. And we have Carson Zide who will be moderating the panel. So Carson Zide works at Vaya Space, and he is the lead Turbomachinery and one second. And yeah, and he has really wide range of background with environmental control and life support systems, as well as propulsion. So to give you the floor. Oh, but before I do that, I would just want to just give a few words about the Space Initiative. So we are a space research company. We're trying to increase opportunity and accessibility to space research all over the world. And I will be answering a few questions about the Space Initiative at the very end, depending on time. And if not, we will be posting everything on our website next week. So, and the meeting is recorded, of course. Everything will be uploaded on the website. So without further ado, Carson, the floor is yours.
Okay. Well, thank you, Sarah. So I'm just going to share my screen real quick. All right. Can you see the presentation?
Yep, sure.
Yes. Mm-hmm.
Okay, so to summarize this panel's topic, space transportation systems, you can kind of break it up into three categories, really, of space transportation. So there'd be like surface to orbit, space to space, or space to surface. In the case of this particular panel, we're primarily going to be talking about space to space, considering it's a space transportation. So this type of category. And to give you some examples, space transportation use cases, deorbiting, orbital space debris, rideshare, station keeping, transitory orbits, and on-orbit servicing, asteroid mining, and most importantly, the moon, Mars, and beyond. And stop sharing that. With these cases in mind, let's introduce our panelists. So to start with Vanessa Clark. Vanessa is with Atmos Space and is an aerospace engineer with a wide range of experience in robotics, human spaceflight missions, specialties in nuclear electric propulsion. Vanessa has a passion for promoting sustainable space utilization and realizing next generation power and propulsion technology. Our second panelist, Julien, I'm going to try here, Vaudolon. Vaudolon? Nice, great to hear. Julien is from Exotrail, an aerospace engineer and space enthusiast with a PhD focused on experimental characterization of Hall effect thrusters. And he's a pilot. And our third panelist, George Salazar from NASA, is a highly decorated electrical engineer for his innovative work on human system integration. George is responsible for the SpaceX Dragon capsule and Boeing CST-100 crew vehicle interfaces. And now our final panelist, Sergey Galkin of Space Telescope Science Institute, is an aerospace and mechanical engineer with hands-on experience with propulsion systems as well as ISS onboard healthcare systems. As I'm sure the audience can tell, this panel will provide us with some very interesting thoughts for today. Now let's get started. So Vanessa, to begin with you, based on your specific knowledge and expertise, what do you think we should be prioritizing in space transportation systems and why?
So first, thanks for the invitation to participate on this panel today. Before I answer the question, a little more background. So I started in launch vehicle design, moved into space agency research, and I was really focused on deep space missions. So we were trying to work out how to get to Mars as fast as possible, how to increase capabilities for deep space exploration. So looking at things like out-of-planet sample return missions and interstellar missions, which just aren't possible today with the technologies that we have. After that, I moved into onboard satellite design and then eventually Atomos space. So I've had a broad range of knowledge. So I'm going to interpret your question as, what should we be prioritizing on for deep space exploration in terms of space transportation systems? If we want to talk about commercial needs, we can definitely dive into that. But from my experience, the propulsion technologies that we have available today are really an evolutionary dead end. If you look at how to get to Mars really quickly, so a sustainable timeline, so within 2 to 3 months rather than an Earth-Mars transit of 6 to 12 months. If you look at getting a probe to Jupiter or the outer planets in 12 months or less, and then having enough propellant on board to do a sample return. What we have today just doesn't cut it. So we were looking specifically at 2 different technologies that can enable this type of transfer or this type of mission in the next 2 decades. So obviously there's a whole bunch of research that's focused on really long-term stuff such as fusion propulsion, but looking specifically at propulsion, which is obviously high thrust, high ISP. And NASA has started to put a lot of money into that for their Moon to Mars initiatives. The second is what we're really focused on at Atomos Space, which is nuclear electric propulsion. So looking at megawatt level electric propulsion systems. And the reason why we're pursuing this is it gives us big delta V capabilities beyond what a nuclear thermal system can do. It can take heavy payloads to Mars. It can take probes to Jupiter in 12 months if you design a system that's optimized for that. And it's also probably going to be the first way we really go interstellar beyond what we've done with the Voyager probes. So I've been advocating for nuclear electric propulsion systems development, but with a bent on developing really high performance systems, which need to be really high power levels. So looking at least 1 megawatt of electrical power, but even beyond that. That's something that I think is going to be the locomotive of moving around in deep space in the future. And it's something that we can realize within the next 2 decades.
That was a great answer. I do actually have a follow-up question on that. So you had mentioned that you're primarily looking at electric-based rather than the thermal. So when you're considering doing like maneuvers, maneuvers such as like an orbital assist, and you're actually trying to dip into that gravity right as you're passing the planet, have you considered thrusters that are more like that would be able to react faster, like the thermal ones, or are you just like planning on using primarily?
So for our commercial systems, it's definitely like a different story. A lot of the interesting commercial missions involve moving from circular to eccentric orbits and back again, doing inclination changes deep in Earth's gravity well, which really makes sense to have a more impulsive system. So we have both. But you really need to have a higher ISP system that is only possible through electric propulsion for a lot of missions.
Agreed. Okay. Well, so to move into our next, well, actually, does anyone else have anything to add to that, to build upon? No?
So the one thing I would, if I can, add in, one of the things that Vanessa mentioned are the long transit times to, Mars to Jupiter, etc. And this may have been something that was covered in the physiology and crew health panel last week. But one of the biggest challenges is radiation dosage, right? So, just a little bit about me. First of all, my name is Sergey. My background has been on operations, including crew operations on the ISS, specifically from the crew health and healthcare perspective. And one of the big things that we were tasked with was specifically radiation monitoring, right? So one of the biggest challenges we are facing right now in terms of the longer crew transit times are the fact that all crew members are considered radiation workers, which means that by the nature of the job, they are assigned a certain radiation dose that they cannot exceed during their lifetimes, for risk of increased, oncological or health benefits. So the challenge with the 6 months transit time to Mars, especially coming out of the Van Allen radiation belts and the kind of protection from high energy events in the sun, is that a lot of the crew members will hit their lifetime limit on radiation dosage on a one-way trip there, which also excludes possibility of surface operations and includes the transit, excludes the transit back. So, therefore, I completely agree with Vanessa that like increased improved propulsion systems for faster transit times are absolutely a must and necessary for long-term space transportation, just to avoid any issues and reduce the risk to crew members specifically.
Yeah, and if I may just kind of add that getting to Mars, obviously, you shorten the time, which means your vehicles are going faster. Therefore, when you're getting ready, let's say, for example, going to Mars, is to bleed off the kinetic energy of a vehicle going at a very high rate of speed with a lot of mass. Okay, so we're talking about habitats, we're talking about large, let's say, rovers and things of that sort. It's going to be rather difficult to bleed off the kinetic energy. So that's the challenge. Right now, the best we can do in terms of landing a heavy object on Mars, JPL has done that with Mars Science Laboratory as well as Mars Perseverance, which is about 2,000 pounds. And so the mechanisms and the approach that the methodology that they use is at the maximum. So if we start going beyond that in terms of size, weight, and well, more so weight, we're going to have to think of alternative ways to bleed off the energy of a high velocity vehicle, if you will, going to Mars, and then slowing it down and then enter the Mars atmosphere. So that's another challenge for the space transportation area.
See Vanessa smiling because, as I believe that is also an advantage of the electric propulsion style of nuclear propulsion, because you don't have
to. It does depend on the transit method you choose, but a lot of nuclear electric concepts also have an impulsive stage to get into Mars orbit and slow down. But my job is to get you to Mars, not get you on the Mars surface.
Great to hear. Great to hear. So, anyone else have any addition to that question? No. Okay. So, Julien, how do you envision the future of space transportation systems 10 years from now?
Well, if you take all the data that are available from the different markets, you end up with about 27,000 satellites that are going to be launched or expected to be launched by the 2030s. So it covers a wide range of needs. It's climate monitoring, connectivity needs, geopolitical motivations lately, the sovereignty of data, the exploration needs, and so on. And all of this today is possible because we have a dramatic decrease of cost of accessing space. There is more equipment, platform, software, launcher offers than ever before, and it keeps unfolding, in fact, at an amazing rate. And 10 years from now, I think that all these governmental, commercial assets will require mobility solutions, and that without some logistics, as we have on Earth, this market may simply not thrive as we would expect. And let's take two examples. I have two examples in mind to illustrate that, from which we can make a parallel. First, if you consider Amazon, Jeff Bezos has explained that he succeeded Amazon because there was already infrastructure. So the credit card already existed, the post office already existed, carrier companies already existed, and should one of them have missed, I don't think maybe Amazon wouldn't have been the same success than what it has been. So this is one thing, and consider also in a space on space market constellation of satellites such as OneWeb, Starlink. You need ground infrastructure and tools to operate those satellites in very efficient way. You don't want to have one guy controlling one satellite. You have to automatize as much as possible the orbital operations, or you will not have a sustainable and scalable business. So I think the future is all about having what we have on Earth, which is services to propose to satellite operators so that they can effectively make their business models, their business case. So the keyword, in fact, is logistics. We have DHL, UPS on Earth, stuff like that. We have to have that in space. And that gets translated in several forms. So, for instance, what we do in Exotrail is that we have the vision of developing a suite of solutions, a mobility hub with various propositions. So you can, let's say, use a software dedicated to missions design or missions operations for constellations. You can use dedicated propulsion hardware, and as Vanessa mentioned, I think electric propulsion is one of the key technologies in space to do that. And we are also developing a space van, which is typically transportation of satellites, which don't have either the propulsion capability or the delta V on board that is necessary to perform their mission. So logistics, services, operating fleets of servicing vehicles. I think that for these 20,000 satellites expected to be launched in 10 years, 10 years from now, this is the real key, in fact.
So to summarize that, if I'm understanding correctly, it's the software and hardware infrastructure is really what's going to build up, and the navigation systems of these satellites, as well as the actual ability to produce these higher end components. Okay. Does anyone have anything to add to that? I really like that answer, by the way, Julien.
So I have something to add. So we have, as a company at Atomos, very similar thinking to Exotrail. And one thing that we've been talking about is that in 10 years, large delta V maneuvers for commercial satellites should be performed by third-party systems like Exotrail's space van, or like the larger systems that we're developing for commercial application. A satellite does need onboard propulsion in a lot of cases for station keeping, collision avoidance, end-of-life disposal, but it doesn't need to dedicate 50% of its launch mass, and in some cases tens of millions of dollars, to a bespoke propulsion system that is used once to do its initial orbit raise. And so it does make sense to have this outsourced delta V in space and have a sustainable space logistics infrastructure. And at Atomos, we see that developing these systems and the technologies for that as a good stepping stone to some of the deeper space exploration missions that NASA and other agencies are also exploring.
Atomos really is making some incredible technology. I agree. Both of you really are on track about what the future's holding. All right, any other comments on that? Matt?
So just to throw in a little perspective from the kind of the big airspace, NASA project side, I completely agree that commercial solutions to current existing problems will definitely manifest themselves to a much greater extent in a 10-year timeframe. But I think the biggest benefit of that, or one of the biggest benefits of that, is that it allows for the kind of quote unquote larger aerospace organizations and government organizations to be able to focus on kind of pushing out the boundaries, like what the next frontier is going to be. So like right now, for example, there are talks of transitioning. Well, it's still up in the air, and George can probably speak to that a little better than I can. But one of the concepts that was pursued was to transition ISS over to commercial partners. At the end of its lifespan. And then you have Axiom 1, which is currently flying on the ISS right now, with the possibility of expanding and developing additional modules to the ISS for commercial applications and commercial use. But what that would do is that would free up the resources from these larger organizations to try to push out for projects that are going to be further out. We're talking Artemis 1, we're talking a lunar settlement, and then eventually, of course, the path to Mars, as it were. And all of that, I think, is definitely going to have a lot of traction within the next 1 to 2 decades or so.
All very good answers. Okay. Anything for you, George?
I just wanted to add what Sergey said, is that for the space industry for the next 10 years, obviously we're going to have to be looking at what's the infrastructure going to look like in terms of depots, for refueling on orbit, and also looking at communications too as well. From a technology standpoint, and it goes back to radiation, I know Sergey mentioned the effects on humans. Well, there's also the effects on electronics. And so a lot of the radiation type of components available right now that are radiation hardened, like for example, what's on Mars Science Laboratory and Perseverance and what have you, are radiation hardened components that run roughly about 10 times slower than your commercial products. And that's one of the challenges that we're looking at. We're talking about AI, we're talking about machine learning and things of that sort, for onboard communications and assessment and decision making. We're going to have to try to figure out a way to get industry engaged in developing radiation hardened components. Our biggest challenge has been, talking to commercial industries that are developing high performance computing like NVIDIA and what have you, is that they'll say how many do you want to buy? Then NASA will say, well, maybe about 50. Well, that's their commercial market is in the millions. So there's no money in them. Even though, and I've spoken to some folks from the NVIDIA that are space buffs, but they said their commercial company plan and all that doesn't engage onesies and twosies, for the lack of for a description of how NASA buys things. So we're going to have to look at that, especially if we start going deeper into space. And certainly they have flown commercial parts in deep space, but they have a limited lifetime. And obviously we want establish a long sustaining infrastructure. Is that reliability is going to have to play into that, and certainly if you're having to replace parts frequently, that cuts into the budget. And of course, the private sector is in the business of making money as opposed to the government that's in the business of spending money. So they have to make sure that the investment that they make is going to be beneficial for the company as a whole, because obviously they have to satisfy shareholders.
Both absolutely very true. So, okay. So moving on to the next question. This one will be for Sergey. So what are some of the biggest challenges? Actually, yeah, let's go this one. For those that are interested in pursuing a career similar to yours, what advice do you have for them?
Well, first of all, I got to unmute myself, So one of the biggest advices that I have is I'm going to actually refer to a couple of things that I've heard from some of the present and past astronauts and the advice that they have given us, which I found, for me at least, works very well. The first one is follow the follow your passions, right? And it may sound cliche, but ultimately it's one of those pieces of advice that implies, identify what particular topics are of interest to you and then pursue those, right? And essentially what that would allow you to do is to become more knowledgeable, more familiar with these topics, and also gain more interest. And the second part of that advice is, find something that you really like to do and become very good at it, right? So pursuing these passions is what lets you become very good at it and become the expert in the field, as it were. So for me personally, space has been on my radar for quite a long time, and I've pretty much developed a very keen passion for it from a very young age, which, through a number of different educational and experience backgrounds has led me to this point, which I'm thoroughly enjoying this point very much, as it were, and a wonderful conversation we're having. So that being said, find out what interests you, what drives you, and start heading in that direction. But then the other part of this is to figure out who is involved in doing these things that you are doing, right? And, if you identify who the leaders in the field are, and then you kind of reach out to them and ask them, it could be anything like as simple as a request for information, something like, hey, I'm interested in what you're working on, can we share some information, or is there any way I can help out? Worst case scenario, that person will say no, but you have nothing to lose and everything to gain from that particular perspective. So that's kind of, one of the pieces of advice I would like to give. Another piece of advice I would like to say is do not turn down any opportunity that is presented to you, right? So, throughout my experience so far, I've held a number of different roles and had a number of different backgrounds. I actually started out in commercial aviation before heading over to space. But all of these experiences have built on each other, and all of these experiences have actually supplemented each other. And everything I've picked up along the way, I was able to use one way or another in what I'm doing as well, right? So, if I said no to any of these opportunities, there will probably be some piece of information that would be missing from what I'm currently doing or working on right now. So, figure out what those opportunities are and kind of go after them and accept them and make the most a learning experience from them. My specific example is actually, I started out as an intern on the space shuttle program when I was back in college and undergrad. And for me, this was, most internships take place over the summer. For me, this was an opportunity to actually do a full co-op. So I would have to skip a semester, right? So it's that trade-off that I would have had to make. Do I continue with my academic studies, or do I put that on hold and try to get industry experience? And ultimately, in the long run, I went for the industry experience option, and I have not regretted that since, because that has set me up for a great number of opportunities later on. So yeah, just to summarize these two pieces of information, figure out what is interest of you, what is your passion, and then pursue that. Reach out to those people who are leaders in that field and see what you can, how you can coordinate with them, communicate with them, and then learn from them, hopefully. And yeah, seek out the opportunities. And when you come across one, definitely pursue it and don't turn it down.
Really is a great answer. In order to find the path, you really do have to do the research and find the resources. It's a great way to state it. And so this next question is kind of phrased for all
Carson, if I may.
Oh, absolutely. Absolutely.
Yeah, if I may, I completely agree with Sergey, and I would add one thing is to don't get anything you're taught for granted. For instance, I think, let's take the example of force thrusters. It's been most of my background, in fact, but I think doing smaller thrusters is harder than doing larger thrusters. Of course, you have specific challenges for both ends, but we've been told, I think all in Exotrail, what you want to do is impossible. You're not going to be able to do a very small thruster. It will not work. It will not be operable in space. It will not be efficient. We will not find customers for that, and blah, 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 and blah, blah, blah. But in the end, we all thought it was necessary at least to give it a try, to see experimentally what it gives, and to have a clear idea, not based on just opinion, but based on facts. And in the end, it turned out to be possible and viable. So yes, take risks, don't get anything you took for granted, and believe in yourself.
Thank you, Julien. Anything else to add from anyone? All right, so this was actually the last of my questions. And so this is gonna, this is really to all of you. Throughout your career, what would you say are the highlights and the lowlights, the things that you really, you look back on as your favorite things that have happened, and some of the things that were the most frustrating that have happened that you've overcame? And we can start with, I guess I asked Vanessa the first question, so Vanessa, if you would like to begin on that, that'd be okay. Otherwise, we can cycle around. I don't mean to pick on you.
So I'm currently a startup founder, so it feels like I'm experiencing my career highlights and lowlights all at once every single day. So I think to answer the question, I'm going to turn it into a little bit of a story. So I'm originally not American, I'm Australian, but I started my career in Germany. And there was a point where I failed to recognized that I needed to get my managers on board with some of my research initiatives. I thought they were going in the wrong direction, so I managed to secure funding without them, and the relationship deteriorated, and it's very hard to fire people in Germany, but they weren't going to renew my contract. That definitely was the low point. You know, in retrospect, like what I believed in and what I thought, you know, the research direction would be was ultimately correct, but I had failed to realize that, hey, I need to prove this to the establishment because, you know, I'm not fighting against them ultimately. They're the people who need to support me. I went from, you know, feeling like I couldn't succeed in my job to leaving the country and starting a new career in the US. So I'd say that that was, you know, in a bad situation like that, I did the right thing. Like I left that organization. I ended up leaving the country and the culture because I felt like I couldn't work with it. But, you know, skip ahead a year later. So this is now 2016. I'd been promoted twice within Lockheed. So I was all of a sudden responsible for 32 engines on board at NASA's, several NASA spacecraft and leading a $400 million contract. Like I found an environment that really worked well for me, that had my sense of urgency, and I, more importantly, found a manager who could listen. And then skip ahead a few more years, and I'm leading a company of about 20. We've raised millions of dollars in venture capital, and we're launching our first spacecraft soon. That is something that, you know, I truly believe is going to push humanity forward in terms of increasing our capabilities in space. But like, still every day, running a company, you know, there are setbacks. And so, you know, ride the roller coaster, and when you're at a low point, like take agency and change things.
Awesome. It sounds like quite the adventure, and I can tell you're really enjoying it. All right. I'll just again go in the same order that we started. So Julien, if you would like to go next.
Yeah, sure. Well, I think that in a company, and especially in a startup, you have, let's say, very good days, very good events happening, and you have also very bad ones happening, which can be in quick succession, in fact. But it's not the hardest thing. I think the hardest thing is working for many months or years without a real vision, in fact, and not a great ambition. I think this at least from my experience was the worst. Technologically speaking, I was working for a company which has wonderful products, which is technically able to do wonderful things, but doesn't have a vision for the future and to move humanity beyond, or at least doesn't give you the motivation to and the vision to move really beyond what already exists. And that's what I came to find in Exotrail, like many new space startups. And yeah, that's my feedback on this.
Thank you, Julien. Okay, and I believe it was Sergey that was the next set of questions. Yes, so Sergey, highlights and lowlights.
So for me, the highlights and the lowlights were probably summed up into one set of experiences, which was going through flight controller training at Johnson Space Center. You know, and just kind of a little bit of a background. Every new flight controller that joins the Space Center has to go through effectively a 6-week-long boot camp, which is a crash course in space station systems and operations. And then after that, the training branches out into the more specific roles that each flight controller would be performing. And one of the biggest aspects to learn was communication specifically. You know, because in operational spaceflight environment, one of the biggest things you have to do is to be, you know, quick, precise, and concise in your communications. So there's actually a formula that the communications follow, which is failure impact workaround, right? In case there's an anomaly or anything that's going on, you identify what the failure is. One of the key things is you determine is what is the impact to that particular failure, which then establishes a priority order as to when this anomaly or failure would be fixed. And then you propose your workaround, which is how do you fix the actual problem. Essentially, all of this boils down to the fact that I had to reinvent myself on a personal level, as a matter of fact, because flight control does not bode well for people who are a little shy and timid, which I was probably more so prior to that experience. So that was one of the things that I really had to kind of dig down and find some internal inspiration that will allow me to push through and develop those communication skills and operational skills that would allow me to integrate into the team as well. And there were plenty of times when I was going through that experience, thinking to myself, what did I get myself into? And kind of, how am I going to, dig myself out of this? How do I manage these stressful situations, right? So, but ultimately going through that experience and going through the training and the simulations that, we kind of have to go through to train and develop these operational skills, has allowed me to kind of develop those communication skills, be able to communicate on an operational level, quickly and efficiently, and made me comfortable enough with the job where I was actually able to be productive and a, good contributor. And that, of course, that's when the really, nice highlights started coming out, because one of the big things for me, one of my personal favorite experiences was working EVAs, working spacewalks from the front flight control room. And, that was something, an experience that was definitely a big highlight of my tenure at Johnson Space Center, because, being able to not only kind of observe the Earth from, the astronaut's perspective point of view, but also watch along as their workflow and their camera feeds, and actually be able to provide constructive input into the day-to-day activities on the spacewalk was a very large rewarding experience to me. So yeah, that's probably what I would refer to in that particular question.
That's quite a great answer. Now, George, the well-awaited, I'm very excited for the answer.
Okay.
Highlights.
Highlights and lowlights. So let me separate this on the low light. And for the low light, I have to kind of refer back and again, perhaps using a short story, so to speak. The low light was basically evolving myself to where I am right now, given my background. So I come from the ghettos of Corpus Christi. Grandparents had no education. My dad had a fourth grade education. My mom was basically second grade education, orphan. And so the education aspect in my family was not very big. I graduated in the lower 20% of the high school graduating class. When I wanted to return to school, I failed miserably the scholastic aptitude test. But a junior college took me on a probation basis, and I passed with flying colors, and then transferred to the university where I first started out in college technology, which supposedly was easier than engineering, but I wasn't happy, so I transferred over to engineering. And when I did transfer over to engineering, also had an opportunity to work in industry part-time while I was going to school. So the combination, again, the electrical engineering degree, working hands-on as electronics repair technician, as well as engineering, manufacturing engineering. When I interviewed with NASA, they liked my hands-on experience, probably more so than my GPA. And I came to work there. So it was an evolution, if you will, going from where I first started. And I could probably talk all day on that. But basically, it was that evolution, if you will, of evolving myself to where I am, where I was, and where I am right now. From a highlight standpoint, I have to say, they talk about, the first impressions always are long lasting. So my first impression, I always consider the highlight. The right about the second year that I started at NASA, they gave me the task of being the project lead for a government furnished equipment, meaning that the government builds and designs and certifies the equipment for flight on the space shuttles, controlling the closed circuit television cameras by voice. And so I wore different hats, and it was, talk about learning from the seat of my pants. I was doing some design work, but I was also learning about project management and dealing with that aspect, and also systems engineering. In fact, that's actually what got me into systems engineering, that eventually 16 years after I got my double E degree, I got my master's degree in systems engineering. And the highlight there was the fact that I got to do a lot of things. I got to do design. I got to work with the safety folks. I got to work with folks at the launch facility, the Kennedy Space Center, installing the flight hardware system on the space shuttle, which I felt like a kid inside a toy factory, if you will, when I went inside the Discovery vehicle and installed the system and checked it out and all that, and working with a couple of astronauts too as well. So I have to say that's my highlight. I'll never forget it, and I've had other successful things along the way, but again, as they say, first impressions are long lasting, and I have to say that was my first impression.
Incredible. Thank you for sharing.
Sure.
And that closes up my questions. Sarah, would you like to, should we move into the audience questions?
Yes. So we did receive a couple of questions from the audience that I will go through now. So George, we have a question for you. How will lunar transportation companies become sustainable businesses beyond NASA contracts? So that was a question.
I'm sorry, who was that question for?
How will lunar transportation companies, in your opinion, become sustainable businesses beyond NASA contracts?
Oh, the lunar sustainable commercial companies are going to have a major challenge, primarily because of the lunar environment. The regolo there is very abrasive. Mechanical systems will take a beating. In fact, Gene Cernan said it best. He said the biggest challenge of the moon landing was more so the dust than anything else. And then, of course, the radiation environment. So sustainability is going to be a challenge, and that's why the Artemis program is going in a kind of a phased approach, is to how to live and learn on the moon, and seeing what the reliability is going to be of these systems, and how to mitigate the effects of the lunar environment, dealing with moonquakes. Few people know there are moonquakes on the moon, and so you're going to be cautious about that. If you're going to be developing systems that are very sensitive to vibration and all that, obviously it has to take into consideration. Certainly, if you're going to be on the other side of the moon, where it's dark, you can't depend on solar panels, and so you're going to have some kind of energy storage device that perhaps is cost effective, but can last a long duration of the mission. So there's a lot of challenges, for the commercial spacefaring companies, and one of the things I have to say about commercial companies, because I work with SpaceX, is that they're very agile, and they see a problem and encounter the problem, and very quickly try to they'll come up with a solution. So hats off to the commercial sector, but it's not going to be as simple as just going to a space station as we do right now. Obviously, you don't have to worry about dust per se, and the radiation environment there is rather benign because of the Earth's magnetic field, and that's why we can fly commercial parts for the most part that pass what we call high energy proton testing. So it's going to be a little more challenging for commercial companies going to the moon, especially in a sustainment fashion.
So I have something to add to that as well. So talking about the market opportunity for commercial companies, besides direct contracts with NASA, I think that George brought up a great point with the ISS. And so obviously we've had the COTS and crew programs that are being extended for ISS. And now we have NASA's commercial LEO destinations programs. And these new programs have been designed for NASA to off-ramp at some point, particularly commercial LEO destinations. And what we've seen with these programs historically, looking at COTS, for example, is that an entire ecosystem starts springing up around them. And so with commercial companies providing add-on services to what Cygnus or Dragon are able to offer, and deploying payloads from the trunk of Cygnus. And then a whole new industry and ecosystem has sprung up around integrating payloads for those missions. And some things that we're seeing with the CLIPS programs and other lunar programs is that commercial companies are looking at, hey, what infrastructure does NASA need and who could be the commercial providers? So some of our prospective customers who are looking to operate in cislunar space, for example, are providing navigation services or communication services or lunar surface imagery. So there's a whole ecosystem that's springing up to support NASA, even though NASA is the anchor customer for all of these services. Once, let's say, direct NASA contracts start fading, we'll probably see some sustained commercial services, particularly navigation and communication. And for us, companies like those are our anchor customers. So I think NASA also is very aware of what ecosystems they're producing with all these contracts and all these initiatives, and are setting them up in ways so they can be self-sustaining once NASA stops being 100% of the revenue and goes back to what they are broadly across industry, which is between 10 and 30% of the potential revenue. So I'm really bullish in believing that a lot of these initiatives can be self-sustaining, but we do need NASA's funding and NASA to lead the way from an architecture and technology perspective to have this infrastructure in place so that we can have a bustling commercial economy there as well in the future.
Yeah, that's a really good answer, actually. Does anyone else have anything to add? Or... Okay. We have a few more questions here. So, Vanessa, there's a question for you. So it asks, who are the competitors and what risks are associated with your technology, it being nuclear, and with offensive DoD use cases for transportation vehicles?
So in terms of the competitive landscape, this is a really, it's not a new concept, but the market has finally matured where it's becoming really interesting. And so while we are building larger orbital transfer vehicles, there are tens of companies who are looking to build them as well, including Exotrail with their space van. We're definitely targeted either higher delta V emissions and heavier payloads. So there's a little bit of a difference there. We're not direct competitors. So it's probably a quick Google search and you can find at least 10 companies that have received venture capital funding in this area. But I want to highlight some misconceptions for what competitors are. So one thing that we get asked a lot is that, aren't small launch companies your competitor? And the answer is ultimately no. No, not at all. They have a really great application for getting a small payload to low Earth orbit if it has a very specific destination. So if it's an uncommon LTAN or inclination, a small launch vehicle is a great application for that. Also for a responsive launch for the Department of Defense in the US and internationally. Another question that we get asked all the time is like, isn't Starship going to compete with your system? And the answer is also no. If you look at what Starship has been optimized for, it's completely suboptimal for transportation of payloads of around 1 metric ton to 10 metric tons in the Earth orbit sphere. If you look at the propellant it needs to consume to do a mission like that, yes, it could do it really well, but it would cost an order of magnitude more than an optimized orbital transfer vehicle such as ours. So, but again, it's really exciting, and there needs to be an ecosystem with multiple players able to offer these services, because we're asking satellite operators to get their stuff to space in a completely different way. And so if there's only one commercial option for that, they're not going to bake that into their design baseline because there's just too much risk. You can't have supply chain and vendor risk. There's just one vendor who can do a certain thing. So competitors are good. Second part of the question was technical risk. So we are targeting nuclear electric systems. And for that, it's not just building a reactor and launching it to space. There's also everything that needs to work with the reactor. So the shielding, conversion system, thermal management system, and of course the propulsion system. So our goal as a company is to fly most of that in space before we even develop a reactor. So our first systems are high power solar electric propulsion. And some of the big risks that we're actually burning down right now are things like thruster lifetime, rendezvous and capture of client satellites, and dealing with dynamic center of gravities without burning too much in terms of ADCS propellant. Another big non-technical risk that we're also looking at right now is the regulatory environment. So one thing for our first mission that is currently critical path for launch for us is licensing with the FCC. There is currently in the US, FCC really wants you to operate in a fixed orbit and as an orbital transfer vehicle where it's our mission to move between orbits. Finding a really good pathway for approval is currently a work in progress. I think, and then the last part of the question was about tie-ins to potential offensive capabilities. So there are definitely initiatives in the US that are looking at two aspects of our technology. One is obviously very capable propulsion systems, but that's more defensive. So like, hey, there's something weird happening in deep space. Like we want to go check it out and see what's going on. And to be able to respond to something like that, not knowing where it is beforehand, you need to have a system that has a lot of Delta V on board. So it's more space domain awareness rather than any offensive system. The second thing that the US Department of Defense and definitely other space-focused defense agencies around the world is looking at is being able to manipulate an asset on orbit. So I think there's been a lot of discussion, maybe not in this forum, but definitely in some of the panels that I've been on before. It's what China accomplished with their deorbit of one of their geostationary satellites. And this satellite was tumbling, it was defunct, they managed to capture it and then move it out of the way. For a lot of agencies who still rely on multi-billion-dollar assets that are a single point of failure for things like communication systems, navigation systems, missile warning, like the ability for a potential enemy to come and grab that object and move it somewhere else is really threatening. And so that's one aspect of the technology that's getting a lot of funding in the US Department of Defense. But there is some silver lining here. The US government funded DARPA to work out some rules of the road. So obviously there's going to be some rendezvous and capture of satellites that's nefarious. Let's make some rules. So if someone deviates from that rules, we have cause to point them out and say that what you're doing is not okay. And so there's an international consortium called CONFERS that we're a part of that's trying to work out how do you approach a satellite in a way that is collaborative, is cooperative, is pre-planned, and that everyone has the correct notification that that is going to happen. So it's not misinterpreted as a defensive or offensive action. And because of this international consortium, we're really increasing international collaboration. We're also increasing standardization, which will allow more rapid adoption of in-space servicing. So some of the things that Julien had also mentioned at the start of the panel. So there are good things coming out of the fact that it could be a potential military technology, and that is really standardization and, surprisingly, international collaboration.
Yeah, that's actually an incredible answer. And competition is very healthy to have, because if we don't have that, we don't have the incentive, to progress and to, try to find new solutions, to the problems that we're currently having. Otherwise, things would be a little bit more stagnant, and we wouldn't have acceleration in that. So yeah, thank you for that. Julien, do you want to add to that?
No, I'm just two things. So two completely different things, but I think that companies will succeed in doing that kind of orbital servicing or rendezvous capture and so on will be the companies who master key technologies. For instance, if you look at what happened lately on the Falcon 9, SpaceX severed ties with a spaceflight, which was arranging slots for customers. And in fact, one of the propulsion systems mounted onto that spaceflight arrangement is started to leak. At least we think it's the reason for severing ties, and that clearly shows that we have to master the key technologies that will be embarked on board transportation satellites. And the second thing is that I'm just eager to see nuclear electric propulsion come to reality, because from a technical perspective, from let's say how passionate I am about space and electric propulsion, I want to see that happening. I'm just curious about what's the technical case in low Earth orbit, or even to Mars orbit, because of what George said. You get to a point where you accelerate so fast that in the end you have to slower to break the speed when you want to enter orbit. And in fact, the solar flux is not that small, in fact, between Earth and Mars. So beyond Mars, I agree. This is definitely one key technology. I'm just a bit more, let's say, eager to see what will occur for nuclear propulsion around Earth, given also the regulatory aspects.
So I want to respond to some of these. So getting a little bit technical here. So kind of one of the big figures of merit that's often overlooked with electric propulsion systems that Julien probably knows really well is specific mass, also called specific power, or alpha. So this is how much your spacecraft weighs versus what the electrical power that's going into your thruster is. So what we've found is that a state-of-the-art solar electric system can be 40 kilograms per kilowatt electric, maybe up to 60 kilograms per kilowatt electric. Definitely at the higher end is where our initial systems are going to be. It's very hard to make a system more lightweight and still produce a lot of power. A system like that is still really capable, but it's going to be a little slow. With nuclear systems, we're targeting nearly an order of magnitude improvement, so less than 10 kilograms per kilowatt electric. What we've found with, I think one of the cases you mentioned is Earth to Mars. The crossover point where nuclear electric becomes better than chemical, becomes better than nuclear thermal propulsion is 14 kilograms. With a low thrust system, if you get below 14 kilograms per kilowatt electric with a nuclear electric system, that's also assuming kind of state-of-the-art thrust efficiency and optimized specific impulse for that type of mission. You can actually go lower than that if you have a bigger reactor. So, if you get to a system that is 5 kilograms per kilowatt electric, 1 kilogram per kilowatt electric, this is like super fast transit to Mars, even accounting for like an extra stage where you can impulsively slow down or have air capture, or even use your low thrust system to slow down and enter Mars orbit. Like it's obscenely fast stuff. I think that one of the groups that's published a lot about this has actually been Ad Astra with their Vasimir thruster, which is, I think, a technology a little bit before its time, but would be great in the future. In terms of what we can do in Earth orbit with a nuclear system, one really good comparison case that we ran was looking at mining water ice and propellants from the lunar surface. So there are specific customers who want those propellants in either geostationary Earth orbit or low Earth orbit. And one of the business cases that was put out there by United Launch Alliance was, hey, we want to get 70 metric tons of this water ice to LEO. And when they did it with their ACES upper stage, which is an impulsive chemical system that burned LOX hydrogen, so it was using the same propellant that it was mining, it would have to burn 200 metric tons of propellant to move that 70 metric tons to low Earth orbit. So they'd have to mine, like 4 times more than they actually needed. We stepped in and had a look at the same mission, and to move that 70 metric tons from low lunar orbit back to low Earth orbit, we only consumed 13 metric tons of propellant. So it's like an order of magnitude improvement in some of the economics, even in the Earth orbit sphere. And so that's, one of the reasons why we're pushing on it. But it's, definitely the best technology once you get beyond Earth orbit. And I think Julien also highlighted the regulatory challenges. I don't want to give a long-winded answer, but in 2019 and 2020, there were some updates to US nuclear space policy. So in the US, commercial companies are now allowed to launch space nuclear systems. And they've set clear guidelines for who approves this. In most cases, it's the Department of Transportation. They also set clear safety and materials guidelines. So we went from having Wild West, no regulations other than an executive order from 1976 that said that the White House needed to approve it, to having a framework. And so, 3 years ago, if you'd asked me that, I would have been like, we don't know how it's going to happen from a regulatory perspective. But now the US has taken the step to enable commercial companies to use space nuclear systems.
Yeah, yeah, we actually had a question about that, but I think you answered like that was a really, really good answer. And it's really exciting times that we're living in, I think. So speaking of, how to go about for, choosing what to use for long distance voyages. So what, in your opinion, would we be able to have recharge stations orbiting Earth or the moon to have, long voyages, long distance missions? And what type, because now you've talked about a lot about already, the different, propulsion systems that we could have. In your opinion, for long distances, which one would you choose, or which combinations would you choose?
I feel like I've done a lot of talking, so I will give it to another panelist to take this one.
Well, I think we are several here fond of electric propulsion. I don't think we have today more efficient propulsion technology that can allow to move, let's say, deeper in the solar system than what we have done before for crewed and uncrewed missions. I think, yes, we're going to need orbital refueling, low Earth orbit. There are some companies already developing some solutions for that. Along the way, deeper in the solar system, we could think about extending those capabilities that are rising around the moon, around Mars, for instance. But in the end, yes, I think electric propulsion has the ability to have the right payload to overall mass ratio, so that we can, in the end, move a meaningful mass at destination. Otherwise, I don't think chemical systems are capable to bring the cargo mass we need to long distances. And then talking about variations of electric propulsion, there are several thrusters technology that can do that. Several power generation mechanisms. We've talked about solar panels, but of course, as you go deeper in the solar system, you need nuclear reactors. And I think, if you are not too, if you don't want to move too fast, you can use solar arrays up to Mars, then you need definitely nuclear reactors.
Yeah, so just to kind of add to that a little bit, definitely one of the biggest challenges from a mission architecture perspective for a Mars mission is the kind of the question of how do you sustain the crew on their journey to Mars, right? Because currently with the ISS, for example, we have a resupply flight probably about every month and a half or so. George, correct me if I'm wrong, but we definitely have a crew rotation flight every 3 months or so. And even that, in terms of like energy budget specifically, is quote unquote an expensive endeavor. So for a Mars transfer mission with a currently existing technologies with a 6-month journey, one of the architectures was considered to have like these quote unquote resupply depots stationed along the trajectory, just because of the fact that having being able to carry all of the resources to sustain the crew, radiation protection, etc., is something that is frankly unfeasible. And the energy budget to launch that kind of mass would be definitely beyond the current capabilities, technological capabilities at this time. There's definitely technologies that are being pursued in terms of crew sustainment on board. Like, we have the Veggie experiment on the ISS that looks at plant growth in a microgravity environment, in an artificial environment, and similar capabilities. But ultimately, you either would need refueling stations from an architectural trajectory perspective, or you would need a advance in propulsion technology, such as going nuclear specifically, in order to shorten the flight time, where you will have the energy budget to bring all of your required sustainment materials with you.
Thank you for that. So we have a couple of questions that we have not touched on, and they're a little bit, not too about propulsion. So one is for anyone, basically, if you wish to answer. So how soon do you expect viable everyday space travel to be realized? So just anyone, maybe George, would you like to take that one?
I'm sorry, can you repeat the question? You broke up a little bit.
Oh, sorry. How soon do you expect viable everyday space travel to be realized?
How soon? Well, for robotic missions, not a problem. For deep space missions for humans, that's going to be a major challenge. So, one of the things that I just like to share with the folks is the human element as part of the architecture, if you will. When we talk sometimes architectures, we only talk about hardware, software, and the environment, but humans are part of that architecture. And one of the let's call it the challenges is to keep the human safe, because things like radiation can affect cognitive abilities, and obviously that's a major problem. In addition to going to deep space, we're human, and so the aspect of not only physiological but psychological effects on a human affects his or her performance in operating these complex systems that are going to take us to deep space. And so there's this likelihood, and that's something that NASA's done since the very beginning, is dealing with human error in systems operation. And so, my area is human-computer interface. And so we look at it from a lot of different aspects of, designing the systems, not to perform and accomplish the mission, but also to ensure that the human knows how to operate it properly, and that there are no human errors, because all it takes is just one bad flip switch or something like that can propagate. If you're familiar with the Swiss cheese model of how many things it takes to have a hazard, is the things that we have to look out for in these space missions. It's going to be a small crew, certainly, to maintain the small crew is going to be a challenge in itself in terms of food, water, and what have you. But also because these systems are going to be so complex that these small group is going to have to depend on themselves as well as the onboard capabilities, because mission control is going to be far, far away. Right now, ISS and even going to the moon is not really a big deal. You got even to the moon is 1.2 second delay in RF transmission. You can still communicate with space IS Mission Control Center, and have a lot of eyes and ears watching the systems. Basically, space station has somewhere in the vicinity of 50 plus people on a daily basis watching the systems. So it's just not the crew that's monitoring the systems, but a whole bunch of people on the ground. As you start going further away, you can no longer depend on mission control, to handle problems, to handle situations. They're going to have to do it on their own, and so that's going to be a challenge.
Yeah, and actually yesterday I was speaking to someone who worked on a project that was sponsored by ESSA, and what they had him do was to actually create an AI that is able to detect whatever the crew member was feeling. So they actually were trying to understand how they were feeling, how astronauts were feeling on the ISS, let's say, just to be able to predict, if they're feeling okay, like if they're feeling stressed, or they're feeling, a little bit worried about something, or if they're relaxed, to be able to, understand, and react in that way. And there's a question actually from the audience that is, talks about that. So, in your opinion, what would be the requirements for us to be able to trust in such an AI? In your experience, in your opinion, because with your experience in human system interface, what do you think, where are we in using AI to monitor crew and autonomously recommend countermeasures to mitigate stresses caused by isolation, confinement, and being in this extreme environment, basically?
Computer trust or AI trust is a major challenge. Right now, our experience in human spaceflight has been with what we call deterministic systems that we can predict with their output, for the most part, can predict how they're going to respond to commands and things of that sort. AI is a little funny beast, because it keeps evolving over time, and so the what we call verification, which basically says that we build the system right, and validation that we built the right system, becomes somewhat of a challenge, because AI changes over time, and so how you continuously verify that what it did and what's it doing is what is the right path. And also there's this whole thing of AI bias, okay? And the AI bias is somewhat related to who programmed the algorithm for this, and was there a certain bias in terms of programming the systems? So the whole aspect of AI trust, computer trust, is another area that that's it's a tough cookie to tackle. But I'm sure we'll get there. There's a certain amount of AI already being done in space, but for the most part, it's not anything near what we're talking about for a deep space mission.
Yeah, it is very biased. Like I've read a lot of papers that talk about this biases, and because also, let's say it depends on, where the location of where that AI was created actually had a huge influence on, how it was performing, how it was predicting, because it depends on the data set they're using, and maybe sometimes the data set is not wide enough, and let's say they're using only, let's say if we use data sets that only include men for a specific thing that has a majority of men working in, let's say, then the results are just very, very much biased. So yeah, I do agree, it's still a very it's a whole other topic. Yeah, it is a tough cookie. Yeah, I totally agree. So we have, I think, one more question that I think we can answer. And this one is for George. So, is NASA interested in the development of medical drones for the Artemis mission?
Medical drones. Okay, I'm assuming that it's some kind of medical. I guess I think of Star Trek Voyager, the hologram doctor. The whole aspect of medical is another major undertaking related to the radiation effects and all this. Astronauts that get sick or even injured on another planet. And again, going back to what I mentioned about the Artemis program and the proving ground, the moon being the proving ground for a lot of technology, is to basically how do we deal with again, AI systems comes into play, is diagnosing properly the astronaut and what's wrong with him or her. And then there's also the radiation effects of the equipment that's going to be needed for medical attention. I was at a conference. It's called Human Research Program, which is a major undertaking that NASA to understand what are the risks are for deep space missions. And that was a gentleman presenting, medical system infrastructure, if you will, for deep space missions. And I mean, it was a huge system. And I guess I was thinking in terms, of to me, it looked like the Google farm of servers, a whole bunch of systems, basically working collaboratively together, to analyze an astronaut and even perhaps do let's call it robotic operations in case there's, the person suffers some kind of heart problems or what have you. And so, I think it's a great idea to start doing and having maybe the commercial industry get involved with developing some kind of medical systems uh, that we need to start proving on the moon. That's the place to do it. And because that's going to be the environment that they're going to be doing. And then, of course, going to Mars. So I think it's great. There's going to be some challenges in terms of technology, but I think it's an opportunity for space commercial companies to get involved with.
Yeah, there are some new ideas that I saw also coming up from, I think in the UK they have a lot of, space medicine things that where they're trying to create surgical systems also, in orbit, and you have a lot of different, that's not super related to this, like it was kind of more related to, the human health and performance panel, but it's kind of a little bit, there's a lot of systems that can be integrated, inside the spacecraft. So we finished the questions that came from the audience, but do you think there's a topic that we didn't really cover that you wish to, talk about, that's, from your experience or from your, previous projects, or something that you think is interesting for, people who are listening to know about?
I have something kind of interesting in our chat. Someone asked the question, how critical will it be to develop space weather models to predict solar coronal mass ejections and solar flares to protect space assets and astronauts? What are the sensitive space transportation systems that are vulnerable, and what can be done to protect space stations' planetary habitats? So like solar weather, I'm sure y'all are really familiar with. Yeah.
So I can take this one. The predictive models that we currently have right now are actually sufficiently good enough to give enough of an advanced heads up to the crew on the ISS in case of a coronal mass ejection or a high energy, high particle effect. That way they can kind of take shelter and reduce the radiation risk to their themselves and human physiology. So I mean, not to say that these models can't be improved, of course, but in terms of like the current observing and predicting capability that exists right now, I think it's sufficiently enough to kind of give enough of a heads up and enough of a warning where proper safety measures can be taken. And of course, these come from a number of other missions that are involved with solar observations, such as like the solar orbiter, the solar dynamic observatory, things like that. And then, of course, the second part of the question is the protection, right? And the question is, how do you kind of keep the crew safe, right? So on the ISS itself, currently there are, first of all, it's protected by the Van Allen radiation belts, the Earth magnetic field. So that definitely reduces a lot of the impacts from the, any high energy events that may occur. But at the same time, there are portions of the station that are hardened specifically for radiation, such as the lab module, which is like the central module in the U.S. segment, and then the Russian service module, which is Zvezda, which is at the quote-unquote tail end, as well as the crew shelters themselves. The crew shelters and like the crew cabins have some levels of radiation protection. So in the event of high energy event, or particle discharge rather, the crew can take shelter and they can actually be safe and minimize the risks of getting radiation exposure and acute radiation poisoning. And then of course with that comes the ability to treat that levels of acute radiation poisoning and the radiation exposure, which is where that medical interface with the ground comes in. So but that's the ISS, right? This is low Earth orbit. If we project it out to the moon, for example, with the moon, one of the biggest aspects is the fact that you're out of the Earth magnetic field, so you don't have that level of protection anymore. So in terms of, that's something that was probably covered in the space architecture panel, but, in terms of keeping the crew safe and keeping the habitats radiation hardened, there's a number of technologies and kind of like proposals that are, being talked about at this time, one of which is possibly utilizing, lava tube formations and like natural geological formations on the moon to shield the habitat from the effects of radiation and like a coronal mass ejection. The other one is, possibly encasing the habitats, in lunar regolith and, putting them underground or partially underground in a sense, because regolith actually turns out to be a very good, radiation protection material. So, and the European Space Agency actually has a number of projects that they're working on currently to try to figure out a way to perform laser sintering and, develop construction materials from regolith specifically, for those applications and for those purposes. So, but that's inside the habitat, right? Of course, the whole point of going back to the moon is, that way we can get out and explore a little bit. And, one of the things that I was involved with the JSC was working on the XAMU and the specific aspect of radiation monitoring within the suit itself. And then also, what happens if you're like about 4 hours into a 6-hour EVA and you're X amount of distance from your habitat and suddenly you have a coronal mass ejection, right? What do you do? So a lot of it becomes operational, right? Like, first of all, individual crew monitoring is a very, very important aspect of this, where, you can have area of effect monitoring, let's say from your lunar rover that has a radiation detector on board and says, well, this particular area received X amount of rads from this coronal mass ejection. But, it can vary crew member to crew member because, a crew member that's, for example, shielded by a geological formation, or is crouching down can receive a lower dose than the crew member that's kind of standing out in the open, right? So individual radiation monitoring and calculation of how much dosage each crew member accrued is a very important aspect in terms of determining overall crew safety and crew health, right? And then at that point, it also becomes an operational challenge. One of the things that was discussed was possibly like grabbing some sort of a entrenching tool and digging shelter kind of in the lunar surface, because once again, you have a few minutes, like, before your coronal mass ejection actually reaches the destination. So, you try to kind of shield yourself in any way you can. Akin to surviving a nuclear blast, if I may say, but it's a very multifaceted problem. So I think for long distance space flight and kind of destinations that are further out, it probably isn't much of a question of prediction, although, better prediction methodologies that give a more advanced warning time would be beneficial. But it's also a question of mitigation. How do you protect, and, what kind of sheltering options do you have in the event of a large high radiation event? So,
can I add additional perspective to what Sergey said? So, yeah, another thing, again, I'm not a human spaceflight expert. I think a lot of our knowledge of the effects of radiation on the human body are based on acute dosages. So one of the really important things that we're doing on the ISS right now is like, okay, what about lower exposure levels over a longer duration? Like, how does that affect human anatomy? So we're still learning, like, where the safety line is going to be in terms of deep space missions. And that's like a really important thing that NASA's doing right now. Second thing that is a slightly different perspective was Sergey's point on modeling and prediction. So space weather has other effects other than on astronauts' health. And so there are two that I want to highlight here. So people in the audience may have heard of a SpaceX Starlink launch failure, where they lost, I think, 50%, 2/3 of the satellites they launched. And that was because they had heard from NOAA that there was a space weather event coming, and that it may affect atmospheric drag. So as Starlink satellites, they're launched into an orbit that has a very, very low purity. And then they do the orbit racing from there. With such a low purity, which is also something that we do and will be doing with our systems, drag can increase, and it may increase to the fact where the satellites onboard propulsion systems can't overcome it. So for our commercial operations, we really care about good prediction of space weather because of atmospheric drag and being able to go down to lower orbits. So our model makes a lot of sense if we can collect satellites and rendezvous with them in low orbits. But obviously we don't want to risk our orbital transfer vehicles and assets doing that. So prediction for us is really, really important. And the effect of solar weather on atmospheric drag was something that I wasn't aware of until we were looking at some of these really specific mission cases where we're trying to get down to 200 kilometers per G. The other thing in terms of space weather and space radiation that we really care about as an in-space transportation provider is what was mentioned before in terms of resilient computing systems, but also solar array performance. The solar array degradation due to radiation exposure is a really big issue, and it's also one of the technical challenges that we're working on for some of our missions where we go from an orbit like LEO to MEO or GEO into space, having to pass through the Van Allen radiation belts. And then space weather also really affects the solar array lifetime. Having degradation of solar arrays won't be enough to kill a system like this, but it would really affect the performance. So instead of getting 20 kilowatts electric, you may just get 16, which is potentially enough to slow us down that system can no longer be commercially viable. So we're looking at self-healing solar arrays and solar panels, modes that we should go into when we're experiencing higher than expected radiation, and how to optimize missions to reduce radiation. So how to avoid some of the worst aspects of space weather and the Van Allen radiation belts. So just some other aspects of space weather prediction as they relate to space transportation systems that I think add to everything Sergey said before.
Yeah, those are really important topics that I think, yeah, it was really good to talk about now.
I was just going to say, just one point. So, space weather, predictions is good. The other one, and it's getting worse and worse, is space debris and trying to dodge all the junk out there, if you will. That's I can't tell you how many times station has to avoid the impact with debris, and it's not getting any better. So I think commercial industries would do well to find ways to clean up the trash, if you will, in space.
I would say that international regulators would do well to create financial incentives for us to clean up the trash.
Yeah, that's a good answer. Yeah, hopefully we
Well
do have
stated.
that.
Yeah, I know I'm being a little cheeky.
We have a few more.
It's a tragedy of the commons. It's like global warming, where everyone is contributing a little bit to the problem, and everyone needs to work together to make it better. But there aren't incentives yet to do.
Yeah, thank you for that. That's a very important point that I think we really do need to work together and to make that happen. We do have a few more minutes left, but if you have anything else that you'd like to share before we close this off. Okay. Well, I'd like to thank you. Sorry, George, did you want to say something?
Well, I just want to say, thank you for inviting me. I really learned a lot from the panel, and so I appreciate the invitation. I appreciate the dialogue that occurred here. Very very informative, and I glad I was part of it.
Yeah, thank
you.
Same comment here, and thank you to the panelists who were really interesting.
Thank all of you for coming. It was a lot of fun to do this.
Yeah, thank you all very much. Just wanted to say that, yeah, it was a great learning experience and definitely provided an extra additional perspective on some of the problems that are kind of faced, both in manned and unmanned spaceflight environments. But also definitely a large thanks to Sarah for organizing this panel together, and to Carson for being such a wonderful moderator.
Yeah, agreed.
Thank you so much for taking the time out of your Saturday, and I know it's a day off today, so thank you so much for spending it here with us. and for sharing your knowledge and experiences. It's been extremely interesting and informative. And thank you so much, Carson, for moderating as well. And thank you all for joining.
I had a great time. I appreciate it. And
Yeah,
great Mars
thank you.
poster, Vanessa, by the way.
Thank you.
Thank you. Courtesy of NASA.
I think I have the same one.
Thank you, Sarah.
You're welcome. Thank you so much for joining.
Yeah, sorry.
All right.
Bye-bye.
Thanks
Thanks.
all.
All right, thank you. Enjoy the rest of your weekend and your holidays.
Sure. It was a
Thanks.
nice
Bye.
information from you. Thanks.
Thank you. Bye.
Bye.